Imagine an AI that doesn't just predict the future, it explains it. Not with vague probabilities or black box outputs, but with a single, elegant equation, one you could find in a textbook, one that reveals the hidden law behind the data. This isn't science fiction. It's happening now, and it's changing how we do science. We've built AI systems so powerful they can learn complex patterns from raw data, weather forecasts, stock trends, medical diagnoses. But here's the problem: they're opaque. They give answers, but never why. And in science, why is everything. Enter symbolic regression, the quest to teach machines to think in math. Not just fit curves, but discover the true mathematical laws that govern a system. The kind of equations that capture nature's rules. Newton's laws, Einstein's relativity, the ideal gas equation. But here's where most methods fail. They don't just search for the right equation, they overfit it. They produce monstrous, tangled expressions with dozens of terms, like a cipher written in alien code. Accurate? Maybe. Useful? No. You can't trust what you can't understand. So what if we could build a system that doesn't just predict, it explains? That doesn't just fit, it discovers. That's exactly what researchers at Montana State University set out to do with SeTGAP, symbolic regression using transformers, genetic algorithms, and genetic programming. SeTGAP isn't just another algorithm. It's a team of specialists, each playing a role in the scientific discovery process. Let's break it down. Step 1, start with a trained AI model, one that already knows the pattern. Then ask, how does each input variable affect the output? Instead of treating all variables at once, SeTGAP isolates them one by one. It asks, if I change only x0, what's the functional shape of the response? It finds the functional form, the underlying shape, without worrying about exact constants yet. This is called a univariate symbolic skeleton. Think of it as the DNA of each variable's behavior. Now comes the real innovation. It doesn't pick one skeleton. It generates many different possible shapes. Then a genetic algorithm acts like natural selection. The ones that fit the data best survive, reproduce, and evolve. But here's the genius twist, merging them. SeTGAP doesn't just concatenate equations. It combines them logically, step by step, like building a Lego set where each piece must fit the structure of the whole. This preserves the semantic integrity of the system. The final equation isn't a random assembly. It's a coherent mathematical story, built from the independent contributions of each variable. Finally, the constants. Another genetic algorithm fine-tunes them, not to overfit, but to faithfully reflect the real-world dynamics. The goal isn't perfection, it's plausibility, simplicity, and consistency. And the result? A model that doesn't just predict, it explains. It doesn't just fit, it matches the true mathematical structure of the system. This is what scientists call stability and consistency, the bedrock of scientific discovery. In a study testing 10 iterations of symbolic regression across 4 synthetic functions, F1 through F4, SeTGAP didn't just perform well. It dominated. PySR. In one run it produces tan 1, 0, 44 cos 0, 627 x 0, plus 0.242 plus tan cos equals 0, 893x, 2.117 sin x 0 e x1. That's not just wrong, it's incoherent. A mathematical mess. But SeTGAP. 1 times sin, 1, 0 times x1, plus 0.004. That's almost exactly the truth, simple, elegant, and repeatable. Even under noise, real-world imperfection, SeTGAP holds firm. At 1% noise. Same equation. At 5%. Still the same. Others. They start guessing different functions. One moment a logarithm, the next a hyperbolic tangent. That's not learning, that's confusion. And the ultimate test. Extrapolation, predicting behavior outside the known data. Can it generalize? Can it understand the rule, not just memorize the pattern? For F1, F2, and F3, SeTGAP error was fractional. Tiny. But F4. The error spiked. Why? Because F4 is too hard. It uses 3 unary operations, sin, log, and division, nested deeply. The multi-set transformer that powers SeTGAP was only trained on expressions with up to 7 operations, and at most 2 unary operators. So when it hits F4, it fails, but not because it's broken. Because it knows its limits. That's not a flaw. It's honesty. This is the future of scientific discovery. Not just smarter AI, wiser AI. SeTGAP doesn't pretend to solve everything. It doesn't overpromise. It says, I can find clean, interpretable equations when the data allows it. When the structure is within my reach, I'll find it reliably, consistently, clearly. We've spent decades building AI that sees patterns. Now we're building AI that understands them. SeTGAP isn't just a tool. It's a bridge between machine learning and mathematical truth. Between data and discovery. And in a world drowning in information, the rarest thing isn't more data. It's insight. Thanks for watching. If you like this deep dive into how AI is learning to speak the language of science, hit like, subscribe, and let me know in the comments. What equation should AI discover next? Until then, keep questioning. Keep exploring. Because math isn't just numbers. It's the universe finally starting to talk back.